All right, this is a video for Algebra 2 in our unit on trigonometric functions, video on the sine function. We'll start with an introduction and then do a few solved examples. So I'm showing you a graph of y equals sine theta right here. So this is just the core parent sine function. The independent variable is in radians, and I'm showing you a couple full wavelengths of this function. When I graph a sine function, there are a few things that I like to keep in mind. First of all, just the core sine function is going to bounce between a positive one and a negative one. Okay, so it has a restricted range. It's going to have a midline right on the x-axis. It's going to start on an uphill climb. That's what I try to remind myself about the sine wave. And then after a full period, it returns to that same pattern of what I call an uphill climb. Halfway through, it's on a downhill climb going through the midline, and then at the quarter point and the three-quarter point, it has a peak and a valley, respectively. I call these the 5 key points of a sine function: the starting point, the ending point, the midpoint, and the peak and the valley. Okay, so these are those 5 highlighted points are good points to keep in mind for a core sine function. This sine function has an amplitude of 1, which is half the entire height of the wave, but it's the vertical distance between the midline and a peak, or the midline and a valley. And this sine function has a period, or a wavelength, of 2 pi, just the distance between two identical points, or the length of a full complete cycle of the wave. All right, let's do some examples. But before we do that, I have this animation that I hope shows up on the video. I want you to track that black point on the right-hand circle as it makes its way around the circle, okay? And the independent variable that we'll be graphing is the angle theta between the radius associated with that black point and the positive end of the x-axis. So theta increases, starts at 0, increases to 180, 360 degrees, and just keeps increasing further and further and further. The sine wave tracks the height of that black point above or below the x-axis, and that's equivalent to the height of the red point above or below the x-axis. You can see the red point just tracing up and or tracking up and down the y-axis there. Okay, so how high above or below the x-axis are those 2 points as we wrap our way around the circle? So one thing you can do if you have a sine wave, you can estimate the sine of various angles. First, we'll estimate the sine of 3 pi over 4. So that roughly looks like, 3 pi over 4 looks like this point right here on the x-axis. So it looks like we're trying to find that y-coordinate right there. And to me, it looks like it's going to be about 0.7 or so. In actuality, it's 0.707, but roughly from reading off the graph, it looks like it's about 0.07. What if we wanted to find the sine of a 45-degree angle, and we just had a graph to work with here? So 45 degrees is equivalent to pi over 4 radians. So that looks like that point right here that I just marked off. And it looks like, because of the symmetry of the sine wave, it looks like it's going to be equivalent to the 3 pi over 4 value that we came up with. So the sine of 45 degrees is roughly, again, 0.7. Let me actually make a tiny correction with the first problem I did. If you were to read this, you might think that 3 pi over 4 is equal to 0.7, and that's not the case. I don't want to misconstrue that. So let me write that a little bit better. The sine of 3 pi over 4 is roughly 0.7. And lastly, we can work with, we can try to estimate the sine of 5 pi over 3. That's 5/3 pi. That looks like it would be roughly this point on the x-axis. So we're looking to find the y-coordinate of that circled point down there. So it looks to me like the sine of 5 pi over 3 is roughly negative 0.9 perhaps. It's actually negative 0.87 But reading it off the graph looks like roughly negative 0.9, so close to negative 1. Finding the period of a sine wave, we're really just looking for the length of a complete cycle, okay? And it doesn't matter where you start and where you end, as long as your starting and ending points represent, they capture a full cycle. So to me, I always like to see if I can start just at the 0 point here. And so there's 0, and it looks like we'll capture a full cycle right between those 2 points. So that tells me that the period of this wave is pi over 2. Or 90 degrees, okay, if we're working in degree units. We can also use Desmos here as an example to determine the amplitude of the function, okay? So we'll go ahead and graph this function on Desmos and try to find half the full height of the function, or the vertical distance from the midline to a peak, or the midline to a trough. So let's go see what Desmos has to say here. So there's the graph of that function right here. I'll copy it on over. And it looks like to me that the amplitude there is 2, okay? And we'll see in a moment that we get that because of that 2 right there. That gives us the amplitude, but the amplitude of that function is going to be 2. So let's summarize some properties of a basic sine function here. We won't look at translating or moving a sine function at this point. We're just looking at vertical stretches and horizontal stretches as well, or compressions. So if we have y equals a times the sine of b theta, the absolute value of a is the amplitude of the wave. Remember, the amplitude is half the full height of the wave, okay? So the vertical distance from the midline to a peak or a trough. If a is less than 0, by the way, we'll end up with a vertical flip, okay? That leads to a vertical flip. So we'll just flip the wave across the x-axis. B, by the way, is the number of complete wavelengths or complete cycles of the wave in the space of 2 pi. Okay? So typically in the parent function, B is 1, which means we have a cycle or a period or a wavelength of 2 pi. We have 1 cycle in the space of 2 pi. But if B is higher, we'll have a shorter wavelength, meaning we'll have more cycles fit into the space of 2 pi. If b is smaller, we'll have a longer wavelength. So 2 pi over b then is the wavelength itself. Okay, so we're just taking our 2 pi, dividing by b to see how long one particular wave is, or one cycle. All right, let's do some examples. So we'll graph a sine wave with an amplitude of 2, a period of 4 pi, a midline of y equals 0, and we want a to be less than 0 as well. This is hard for me to tackle all at once, so I'm going to take a piece at a time. The fact that the midline is y equals 0 means that we haven't dealt with any vertical shifting as well, so I'm actually going to cross that off. That doesn't really apply to us at this point. It's a standard parent function type midline. Okay, we have an amplitude of 2. Let's get the period of 4 pi in first. Okay, so let's pretend all we're modifying is the period of 4 pi. So we're starting off on an uphill track. After 4 pi, we have to return to that point. Midway through, we're on a downhill, on a descent through the x-axis. And at our quarter points, we reach our peak and then our valley. So if we just simply had a change in the period or wavelength, that's what our wave would look like, okay? But it looks like we have an amplitude of 2 as well as an a value of less than 0. So we have a vertically stretched as well as a flipped wave. So let's do that, and I think we can do both of those at once. So we're going to start off at 2. We're going to start downhill because we have a vertical flipping happening. and then we return, and then finish the wave from there. So this is what the wave should look like. One thing that's a little bit challenging is when you're drawing your wave to try to make a nice smooth curve that matches what you might see on Desmos or on a graphing calculator. My initial sketch I made right here, that's a little bit of a sharp bend. I don't love that right there. But my final red wave for the final answer, I feel okay that that's a pretty good sketch right there. So that would be my final answer right there. The equation of this wave would be y equals -2 times the sine of 1/2 theta. Okay, 1/2 theta meaning in the space of 2 pi we see half of the wave. Okay, so in other words, in this space right here, we're only seeing half of the wave, right? And -2 deals with the flip and the vertical stretching. Last one here, we're going to graph the function y equals 0.5 times the sine of 2x. So this means our amplitude is 0.5. And this means, let's figure out our period. Our period is going to be 2 pi over b, and in this case b is 2. So our period is going to be pi. Again, I only like to try to modify one thing at a time as I'm graphing, so sometimes I need to sketch a couple graphs. So I'll start the first piece in, let's deal with the, well, our scale is set up so it looks like we have to deal with both things at the same time. So we have an amplitude of 0.5 and a period of pi. Okay, so we're going to start off on an uphill climb, and after our period, a full wavelength, we're going to return to that uphill climb. Halfway through at pi over 2, we're going to be going downhill, and at the quarter points, we reach a peak, figured out from our amplitude, and a valley, a trough. So it looks like we can sketch in a wave from there. And I encourage you to try this on your own, and certainly go to Desmos and check it out as well. I'm going to try to clean up that first bit of it a little bit of a flatter wave as it flatter slope as it crosses the peak. All right, so that would be a graph of y equals 0.5 times the sine of 2x. And it looks like we got through it, and that's a great place to stop right there.